Mr. Taru. In this video, we are going to be introduced or reminded about the correct order of operations. We're going to go through quite a few examples, finishing up with a couple of word problems and an error analysis as our last example in the video. In total, there'll be about 8 or 9 examples in here, so hopefully it'll be enough to get you through your homework. So our basic order of operations is remembered, or at least how I was taught, remembered by a sentence of, "Please excuse my dear Aunt Sally." And I've made capital letters at the beginning of all these words because it's the initial letter or the capital letter that's supposed to remind you of the correct order of your basic math operations. We've got "Please excuse my dear Aunt Sally," or you might have just have heard just PEMDAS. And what that tells you to do is we're going to do parentheses, exponents or powers next, multiplication and division. You can see I have underlined here that they go together. And then we have addition and subtraction. So you see this PEMDAS and you see, okay, well there's 6 basic math operations. Parentheses, exponents or powers, multiplication, division, addition, and subtraction. Well, there's really not 6 levels or 6 steps that you take when you do basic order of operations. There's actually only 4, and that's what this here at the multiplication and division and addition and subtraction is what too many students and adults even sometimes forget. So what do we do here first? Parentheses, or just any grouping symbol. It could be square brackets or anything. You want to perform any math operation that you see inside of your grouping symbol first. And that actually does include fraction bars. They're grouping symbols as well. So what I mean is here, if we have parentheses 2 plus 3 minus 1, then we're going to have to work with the order of operations and see that we have, actually let's change that to a division of 2. We're going to have to look at that and go, well, there's addition and then we have division. Well, you know, we're supposed to divide before we add, but no. We have parentheses, we have a pair of grouping symbols, and that means that we have to work inside that first. So 2 plus 3 is going to be equal to 5, and then 5 divided by 2 is going to be equal to 5 over 2, or let's see here, 2 times 2 is 4, so that leaves us with the remainder of 1, and the answer could be written as 2.5. So inside those parentheses, you want to work that first. Now, if I remind you in looking at that fraction bars are grouping symbols as well, if we have the example of 4 plus 8 divided by 2, maybe you would say, okay, well 4 divided by 2 is equal to 2, and then that plus 8 is equal to 10, or something like that, which would be incorrect. The numerator, the part above the fraction bar, the numerator and denominator, the numerator has 2 terms in it, and the fraction bar acts as a grouping symbol, so you need to act as if there's a parentheses around the 4 plus 8, even though we don't have to write it because the fraction bar is underneath the entire 2 terms of 4 plus 8. Well, so that means we have to add the 2 numbers on top first, so 4 plus 8 is equal to 12. That divided by 2 is equal to 6, and that's our final answer. Okay, then after you clean up the inside of your parentheses or your grouping symbols, or working with maybe the numerator and denominator of your fraction, if you have a large fraction with a lot of operations in it, then you move on to exponents or powers. And that whole thing together, a power is a base and an exponent. Now, of course, the exponent will simply tell us how many times we write that base, and exponents are sort of a shorthand notation for repeated multiplication. So if we have 3 squared, that means that we have 2 of these bases of 3, and I'm going to write it twice, and we're going to put multiplication in the middle of it. So 3 squared is 3 times 3, which is equal to 9. So parentheses first, clean up inside, then you go to your powers or exponents. Now here's where some students and adults even get messed up a little bit. Multiplication and division. As you read the problem left to right, whatever comes first. See, we have to say all these words individually. You know, please excuse my dear, or the order of operations is parentheses, exponents, multiplication, division. that's just like the way we generally say it, and maybe part of it is because of this sentence, or PEMDAS just, falls off your lips easily, but you don't multiply before you divide. These are sort of in the same level or within the same step. You just do whatever comes first. And sometimes you see these problems like on Facebook where they're just trying to, someone's trying to prove to us, hey, you don't really know your math. Where they go, okay, well, what is the correct answer? Well, some people will incorrectly, and maybe we'll do the red first, for being incorrect is going, okay, please excuse my dear Aunt Sally, my dear, multiplication and division. All right, so multiplication is 2 times 6, which is 12. And then 10 divided by 12 is equal to 10 over 12. Those are both even, so they can both be reduced. I can divide the numerator and denominator by 2 and almost run out of room. And we think incorrectly that the answer is 5/6. Incorrectly. There's a reason I'm doing that in red, right? I'm a teacher. I use my red pen to correct mistakes. No. As I read this left to right, the first math operation I see in that multiplication and division sort of level of importance, or not importance, but step, is division. Okay, so 10 divided by 2 is equal to 5. Maybe hierarchy is a better word. And then read left to right again, 5 times 6 is equal to 30. That's the correct answer, not this over here. Okay, so though we say, multiply and divide as you go through the phrase, maybe please excuse my dear Aunt Sally, no, it's together, whatever comes first as you read it left to right, and addition and subtraction is the same way. Again, with the incorrect way first, 5 minus 2 plus 3, okay? Don't get stuck on this AS and think I have to add first, because 2 plus 3 is equal to 5, and so we have 5 minus 5. Well, 5 minus 5 is equal to 0, and that's not what that equals. If you've got $5 in your pocket and you spend 2, as I read this left to right, with addition and subtraction being the last step together that you work with, 5 minus 2 is equal to 3. 3 plus 3 is equal to 6. And there we see, really, with this third and fourth step, where way too many people forget their correct order of operations. Next! Here we have 3 just arithmetic problems, no variables in it yet. We got 4 squared minus 5 plus 2. Okay, of course, we're going to take care of our exponents first, so 4 squared is 16. We got our parentheses in here, and if I read this left to right, I would want to do 16 minus 5 and then add the 2, but with the parentheses, we got to work in there first, and 5 plus 2 is equal to 7. And then finally, oh, and by the way, it is a positive 7 in there. Sometimes we have these two negatives that are touching side by side and they become a positive. How that happens is that between this negative sign and the parentheses, there's a 1 there that we don't really have to write. And it's negative 1 times either 7 or negative 1, times a positive 7 like we have. And negative 1 times positive 7 is negative 7. So that's where that comes from. We have 16 minus 7. If that 7 were negative, it'd be negative 1 times negative 7, which would give us a positive 7, but we did not. So, and then 16 minus 7 is equal to 9. Over here we got a fraction bar, which again is a form of grouping symbol. So we're going to simplify the numerator to be one single number before we divide it by the denominator. And we have 3 times 7, which is 21. We got 21 minus 1, which is equal to 20. And then finally 20 over 15. Both of the numerator and denominator have a factor of 5. So I can show that I'm going to divide the numerator and denominator by 5 to reduce it, or, which is really honestly what I do most of the time in class, or I can factor this and show that they have the same common factor. So 20 is equal to 4 times 5, and 15 is equal to 3 times 5, And then anything divided by itself, 5 divided by 5 is equal to 1, so they cancel out because when you multiply by 1, well, 5 times 1 is still 5, so it appears like nothing really happens. It's the identity of multiplication. And 4 divided by 3 is just 4/3. Or, to write it as a mixed fraction, let's see here, 4 divided by 3 is 1. And 4 minus 3 is equal to 1, so there's a remainder of 1, so it's 1 and 1/3. I'll write that one as a final answer. Okay, now over here we have 6 squared divided by 4 plus 1/2, not plus, times 1/2 plus 5. So 6 squared divided by 4 times 1/2 plus 5. We have an exponent or power. We're going to do that first. 6 squared is 6 times 6, which is 36. Left to right, again, even though we say multiplication, division, addition, subtraction, or PEMDAS, or please excuse my dear Aunt Sally, it's just because we can't say two things at once. So we're going to make sure, remember that multiplication and division are within the same step, and we're going to read it left to right. 36 divided by 4 is 9. And we have 9 times 1/2 plus 5. Now we're getting to the study of algebra, and that means, again, we will be very, very often applying a letter to represent an unknown numerical value or quantity. And that means we're going to do math with letters floating all over the place. And really, you know, if you write your x a little big, this might look like 9x 1/2, which would imply that they all get multiplied together, but it's like, you know, 9x. This is really a better way of writing multiplication now that you're going to start writing variables all over the place, because, you know, is this a multiplication symbol or is it the letter x? It's going to be a little bit confusing, especially if your handwriting is a little bit sloppy. So really I prefer writing my multiplication like this and having 9 times 1/2 plus 5, and I could have written that all the way up here as well. Okay, so how do you multiply with a fraction? Well, that 9 is not appearing to look like a fraction where the 1/2 is, so I don't have the numerator and denominators lined up, so I'm going to write that 9 as 9 over 1, and when you multiply fractions you go straight across the top, so 9 times 1 is 9, 1 times 2 is 2. Put that calculator away, you don't need it for fractions. That crutch is really holding some of you back. Plus 5. Okay, well now I need to add these two terms. Well, 9 over 2 plus, you see what I did with the 5? It's 5. Now, it was just 9 and I wrote it with a denominator of 1. So now I'm going to take that 5. Really, when you're working with fractions, you should just go ahead and make everything look like a fraction. And then you get those numerators and denominators to line up. To multiply fractions, you just go across the numerators and denominators and boom, you're done. But with adding and subtracting, you need a common denominator. That means I need the lowest common multiple between 1 and 2. So 1, you know, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. 2, and then the 2's, the multiples of 2, 2, 4, 6, 8, 10, 12, and so on. We're looking for the lowest common multiple. And that, of course, is going to be 2 because you can really kind of make a 1 into anything. So we're going to multiply the numerator and denominator by 2 to get those denominators to match up. We have 9 over 2 plus 5 times 2 is 10 over 2. And now with those common denominators, which we are not going to add, it's just going to stay at the bottom, 2, and 9 plus 10 is equal to 19. That's our improper fraction. If you want a mixed fraction, well, 2 times 9 is 18, which is almost 19, so 19 divided by 2 is 9, sorta. Well, 9 times 2 is 18, so 19 minus 18 is with the remainder of 1/2, and there's our mixed fraction. Alright, I got 4 examples now coming up. They are going to involve starting with an algebraic expression, which I'm going to give you some values to plug into those, and then finish them up looking a lot like these problems. I meant to point out to you the problems I just erased, that you'll notice that as I did those problems, I only did one mathematical step in each line that I wrote. That means I have to write a lot more, and it might mean that I take a lot more paper up, but it also means I make a lot less mistakes. So your teacher, for a couple of reasons, is asking you to show your work when you work in algebra, hopefully any math class for that matter. A, And that's not a very nice thing, but you know, we want to make sure that you're actually doing the work and not just copying it off your neighbor. Yeah, well, another reason is some of the concepts, maybe not necessarily this section for you, depending on your math abilities, you might find this, but some things that we teach, a lot of things that we teach, we start off in very easy settings. And we teach you how to do certain problems that you might think, I could just do that in my head. But the mathematical steps that it takes to do that problem need to be memorized to be able to do harder problems that you can't just look at and get the answer to, right? I mean, who wants to start every homework problem with or every assignment with the last 3 or 4 problems in the homework that are so hard with so many steps that, you know, probably almost nobody could do them. You start easy and you go hard. Those steps in the easier problems help you do the ones later on. If you've had those steps memorized, if you write those steps at every, you know, in small detail, every single line, you're going to remember them better. This being maybe just more on the arithmetic side, it's just going to help you make fewer mistakes. Okay, so I'm going to help you set these up, getting the substitution in from the values that we have, and then I'm going to step out and reveal the answers one problem at a time. That'll give you a chance to stop the video and try the problems on your own and then check your work. Because when these are done getting set up, it's going to be just like the previous screen. So we have y plus x. Well, y is equal to 5. I mean, because there's nothing I can do here. These are, as we go through our study of algebra, we're going to learn that these are called terms, and they're not like terms because they don't have the same variable in them. So y plus x, nothing's going to happen. That's as simple as this is going to get. But if I take the value of 5 and I substitute it in, I want to evaluate these expressions. Now, when your algebra book tells you to evaluate, that means they're looking for a numerical answer. Like, they don't want a final answer of like 2x plus 7. They want a numerical answer, like 10. So we're going to take these values, plug them into these expressions, and find a simple numerical answer, as simplified as we can get it. So y is equal to 5 plus. Now, I'm going to do this for the rest of it. Every time you do substitution, you really should use parentheses. So let me go ahead and actually go back here to the 5 and wrap it up. Now, why am I doing that? Because of helping you avoid making potential sign errors. I don't think this is really a good one to do this example on. This will seem, you'll understand why I'm doing this more in the next problem. But every time you do substitution, you should take that variable where it was, pull it out, and just write a set of parentheses where it was. So we have a parentheses, okay, well then there's a y going in there, plus, and then there's an x there, and then close the parentheses with an exponent of 3. Really going to help a lot on the sign errors, or preventing you from making those as you do your work. So y is equal to 5, plus, our x value is -2. Okay, now, there's no number out front, there's no exponent, there's no divisors, there's nothing inside the parentheses except for a basic 5. So really in this particular case, the extra parentheses I'm doing they don't really do anything. So we're just going to write 5 and plus a -2. When you first learn how to work with signs and add and subtract negative numbers, we do like that plus negative situation quite a bit. But as we get into our study of algebra, you're going to be writing some problems that are fairly complicated, and the fewer symbols and stuff that you have to write, it's going to clean it up and make it a little bit easier to understand. So let's slip a little 1 in there in front of that plus and parentheses sign and go, okay, well this is a positive and that's a negative. Well, positive 1 times -2 is -2. So this is equivalent. Adding by -2 is the same as subtracting by 2. And 5 minus 2 is equal to 3. I just said I wasn't going to do this, but now I am working this problem out. And then 3 cubed is 3 times 3 is 9, times 3 is 27, or maybe if you're just getting your exponents and powers down, you might want to write it 3 times, and then your final answer is, of course, 27. Now over here, we have 2 parentheses 5 minus x squared. Okay, well, it's 2 minus 5 parentheses, or parentheses where the x used to be squared. I didn't even look at the numbers I'm plugging in, even though it's the same for all these problems. But I just took that expression, took out the x, put in a set of parentheses, Now let's look at what the numbers are. The x is negative 2. Alright, here's one place that students make a mistake all the time. They think that there's a minus there and it's negative 2, so a lot of students will incorrectly write 5 minus 2. But what they miss without this parenthesis idea is that there was a negative in the problem to begin with and a negative coming in from the number you're substituting in or plugging in. They're going to cancel out because this, again, there's a minus here, assumed to be 1 between the negative sign and the parentheses, and negative 1 times negative 2 is a positive 2. And that's just a small example where I'm trying to have you do these parentheses to help you not make a sign error, because it's not 5 minus 2, it's plus. We're going to finish that up. Over here we have parentheses for the x to the 4th power minus 2 times y divided by 12. Or you could write that as divided by 12. Either way is fine. Show your work the way your teacher likes. And the x is going to be negative 2. And our y is going to be equal to 5. And as I step off and allow you to do these problems on your own and reveal the answer as we go, let me just talk about this negative number to an even power with a different number here. Negative 3 squared. Negative 3 squared is negative 3 squared, or negative 1 times 3, which is negative 9. That's not the same as negative 3 squared. Now if I put a negative sign, this is another place where the parentheses are a good place every time you do substitution. If I put the negative inside the parentheses and then have the exponent of 2, negative 3 squared is negative 3 times negative 3, which is equal to positive 9. So this negative is inside the parentheses that has the even power on it, and if you don't watch your notation correctly, you're going to have, again, a sign error in your final answer or somewhere along your work and get your final answer incorrect. And then finally here we have 2 times, our x is negative 2, times y, which is 5 squared, plus 2 times our x, which is negative 2, times 5 squared. And this here too, right? The only thing being squared here is the y, and on the second term, it's the entire base, the entire 2xy that's being squared because of the parentheses. So I'm going to step out, pause the video, reveal these answers one at a time. If you would like to try them on your own, pause the video now and work them out. You'll see I kind of cheated a little bit on that last one. I hope you got the same answers. I kind of handled the two terms separately, whereas here I looked at this term and I did the exponent first, and 5 squared was equal to 25. And I also, on the right-hand term, or the second term, took the numbers inside the parentheses and multiplied them all together and got negative 20. 2 times negative 2, or excuse me, 2 times negative 2 is negative 4, and negative 4 times 5 is negative 20. And then on my left-hand term, I did 2 times negative 2 was negative 4, and at the same time did negative 20 squared, which was equal to 400. Again, that negative is inside the parentheses, so it's negative 20 times negative 20, which is positive 400. So I did one step at a time, but I handled each term kind of separately. So I am sort of doing two things at once in a couple of these lines. I got a couple of word problems, and let's get to them. Oh, I don't know. How about right now? An object's momentum is defined as the product, which we now know after the last video is multiplication, of its mass m and a velocity v. Write an expression for the momentum of an object. Well, this is a problem inspired by the section that I'm teaching out of. I don't like the idea of expression because, well, it's the momentum is equal to that. So I'm going to kind of cheat a little bit and write an equation. Okay, so the momentum is equal to, now technically I'm writing an equation, so like kind of just pretend that's not there, is equal to the product of the mass and the velocity. So it's equal to the product of capital M times, V. Okay, well, it wasn't too bad in the mic. Make a table to find the momentums with a mass of something with a mass of 1,200 kilograms. Okay, so the mass is set, that's going to stay the same, or a constant quantity for this particular problem of 1,200 kilograms moving at, and now the velocity is going to change. So what we really have here is the momentum is equal to 1,200 v. Now we haven't really got an equation yet, so let me just give you a little bit of a preview. We are being given the values of 10, 20, and 25 to act as our different velocities. We're going to later call these our independent variables. And so v is our independent variable, and based on what that value is, we are going to get a calculated value of momentum. So that would be called the dependent variable. And I want to make a table of values. So what I'm going to just simply do here is put something like, how about for a velocity of 10, we get, actually I'm kind of like going to come up with my own table, but let me make sure that my notes match the textbook that my students are going to be using with my class and get a table up here. Alright, that's better. So we've got, well, we have no chalk. Here we go. So we have our table set up. We have our three values of velocity that we want to use. We have our expression of mass times volume, and our momentum is simply going to be the product. So 1,200 times 10 is going to be 12,000. We have 12,000 times 20, which is going to be twice as much, or 2 times 12 is 24, with 1, 2, 3 zeros after it, so it's going to be 24,000. And then finally we have 1,200, did I say 12,000 up here? 1,200 times 25. Well, we already know that 1,200 times 20 is 24,000, and we know that 10 times 1,200 is 12,000. Well, 5 is half of 10, so really 1,200, if I know 1,200 times 10, I can kind of figure out 1,200 times 5 is going to be half of 12,000, or 6,000. Or I can do 5 times 1,000, which is 5,000, and 5 times 200, which is 1,000, which is 5,000, and 1,000 is 6,000. So 24,000 times 6,000, or plus 6,000, excuse me, is 30,000. Okay. For our second problem here, we've got write an expression to evaluate how much spending money you have if you save 10% on your income and 75% of your income goes to bills. Now it says again, write an expression, but I'm going to really kind of start off with words and kind of do some plain language, and it's really going to come out to be sort of like more of like an equation to help us set this up. Now spending money, well, spending money is like what you have left over to buy stuff or do stuff you really don't need to do. Like, it's not for your food, it's not for electricity, it's not for, you know, day-to-day bills. It's just maybe some extra money I have to go watch, you know, go to the movies or something like that. So your spending money is going to be equal to how much you make, or your income, you know, per week, per month, or however you get paid. And now you're going to subtract out of your income, subtract some for your savings. You know, make sure that you have some money left over for when your car breaks down, or help to send your kid off to college, or buy yourself a new TV or something like that. Whatever it's for, retirement. So you have some kind of money, you're going to take out of that your savings, which you're going to put away and not use unless you need it, or put it towards a goal ultimately that's many years down the road. And then you're going to take out some money for your bills. And when you take all of that money and subtract out your savings, which you're just going to do to make sure you have some money for later on to build up some comfort and some security. Take out some bills. That money left over is your spending money that I can put it anywhere I feel like, and it's just for, let's say, enjoyment. Well, let's let income be represented by the letter I. Okay. Now we're going to take out of that some percentage of that for your savings. Well, 10% is going to savings, and we don't ever work with percents in percent form. We always take those decimals and move them back 2 places. So we're going to take our income and multiply it by 0.1. So we're taking that 0.1 came from doing the 10%, moving the decimal back 2 places, and getting 0.1, and we're multiplying. If you want a percentage of a whole, you multiply by that percent. Then we're going to, from our income, subtract out the big part of where our money is going, which is the bills. So we're going to take, again, that income, and we have it figured out from looking at past months or whatever, that about 75% of our money goes to bills. So we're going to do 0.75 times I, and here is our expression, which is our spending money left over. As soon as I say the word equal, really I'm kind of writing an equation, but it's I, our income, minus 10% to our savings, minus 25% that goes to bills. Now, all of these are like terms. There's 3 terms, by the way. They're separated by these subtraction signs. There's 1 here, 1 here, and 1 here, and they all have the same letter. And they all have the same exponent. So actually we can combine what we're going to really be defined later for us, which are like terms, to be 1 minus, and someone's coming, so I'm going to need to pause the video. Okay, so we have I minus 0.1I. Now, we're going to learn later a specific definition called, or define like terms where they have the same variable in them with the same exponent. So I can just do the 1 minus 0.1, which is 0.9. Just going to do one thing at a time. And now we've got 0.9I minus 0.75I, and 0.9 times 0.75, well, 0.90 minus 0.75, 90 minus 70 is equal to 20, and then 20 minus 5 is 15. But I'm doing that mentally, so maybe that's a little bit confusing. How about we take the 9 and we borrow 1 from it? Carry that over. 10 minus 5 is equal to 5, and 8 minus 7 is 0.1, or 1, and then we bring it to the decimal and we get 0.15 I. And, your teacher, this might be a perfect expression that they're looking for, or they may be expecting you to combine the like terms and say your final expression is 0.15 I. I got one more problem involving kind of like looking at some work that's been done and figuring out, is it okay or something wrong? Are these equivalent statements? X plus y squared and x squared plus y squared. I get students all the time saying that these are, even up into my pre-algebra or pre-calculus classes, and it drives me insane. The answer is no. Eventually we're going to be learning the distributive property or FOIL. I don't actually teach the FOIL method, I just teach distributive property. And you'll see, hopefully after learning that, why these are not equivalent. But for right now, let's just remember that when you're told that something is true in mathematics, it's supposed to be true for every single number, every single time, forever. If something works 1,000,000 times and fails once, then it's mathematically false. So I got a couple of values up here that I want to test to see if these expressions are equivalent, and really we're just practicing again our order of operations. Let's see. Are these equivalent expressions when we have the values of x equals 0 and y equals 3? Well, let's see here, we've got x is 0, so we have 0 plus 3 squared is equal to 0 squared plus 3 squared. I'm just simply, plugging the values in that we have into these two expressions, or this one equation with the equal sign in the middle. And if they're equivalent, they're both supposed to be the same numerical value. They're supposed to be the same or equal on both sides. Well, 0 plus 3 is 3, and 3 squared is 9. All right. 0 squared is 0, and 3 squared, again, is 3 times 3, which is equal to 9, and 0 plus 9 is equal to 9. So, looking like we're checking out, okay, that these are equivalent, but I told you my students do this all the time, or tell me this is correct all the time, and it's not. So, while we checked out and for a couple of values, I don't think it's going to hold up for the next one. Over here, we've got, instead of an x value of 0, we have an x value of 2, but the y is staying the same. So, parentheses, 2 plus 3 squared, and I'm actually kind of being a little lazy here, not using my parentheses, so let's just do this. Okay, our x value again is 2, so everywhere there was an x, I'm going to put in a 2. Our y value is equal to 3, so everywhere there's a y, we're going to put a 3. We have 2 plus 3, which is equal to 5, which is 25. But on the right-hand side, we have 2 squared, which is equal to 4. We have 3 squared, which is equal to 9. And the last time I checked, 25 is not equal to 13. So, where's my remote? Because I'm done. I just proved that these two expressions are not equivalent by simply finding one example where it does not work, and actually it hardly ever works. So, I'm Mr. True. Thank you for watching. Bye! Go do your homework.